Okay. All right. All right. Okay. All right. Looks like the stream is on. So, welcome back, everybody. Okay, let's close this. Let's. Yeah, this is good. Okay, let's close that. That's just my blueprint for all these streams. Because let me tell you guys what I'm planning on doing. Um, Hello, welcome back to my channel. These are live streams just so that I don't have to deal with uploading and editing videos. Everything will go up instantly, so it'll just be a few seconds every time. I'm going to start a new YouTube tutorial series going through making neural networks from scratch in Golang. To do this, I'm using a book that I bought a few years ago called Neural Networks from Scratch in Python, or NNFS, as the authors so lovingly call it. It's an amazing book. I got this, I think it was like 2 years ago. Whenever the book came out, it feels like 2 years ago. Maybe it was only 1 year ago. Absolutely incredible book. Absolutely incredible book. I read it. I read all of it, if not most of it, and followed along with it in code. And recently, as you guys know, people that have been watching my channel, I love Golang. I'm in love with Golang completely. Um, so I want to make a tutorial series going through this book, but translating it over to Golang. I think will be a lot of fun. One of the reasons why I think it'll be fun is because anyone that knows anything about neural networks knows that it's a lot of matrices and nested lists, and there isn't really a NumPy for Golang. Those of you coming from Python, you know what NumPy is. It's this awesome library that's used to make matrix manipulation very easy. So there isn't one of those for Golang yet. I think that through this tutorial series, we're going to be building a lot of the features that are found in NumPy from scratch in Golang, which one, super excited to that's a challenge, and I'm so excited to take that on because it sounds super fun. And also to record it and have it on YouTube. Also, this could be the beginning of a very powerful tool in Golang. I know there are a few libraries in Golang that are similar to NumPy, like, what do you call it? Numba, and a few other things. None of them get to the craziness of NumPy. NumPy is an insane library. So we're going to be building something similar to that. And because of that, I'm going to be very careful on how I structure my code in this tutorial series. So there you go. That's a basic introduction out of the way. Moving forward, I want to discuss. What do I want to discuss? Okay, I want to discuss what we're doing in this video exactly. So here I have, this is exactly how the videos are going to look most of the time. Let me hide the taskbar. That would be nice, I think. This is, yeah, no, that's not it. Is there an easy way just to hide taskbar? Like my computer updated to Windows 11, and there used to be a nice little taskbar hiding thing whenever you right click the taskbar, but that's gone now, apparently. That's annoying. Taskbar behaviors, automatically hide taskbar. Great. Okay, so now the taskbar is gone. That'll make this a much nicer environment, I think, to code in. Yeah. So this is exactly how the layout's going to be. Split screen down the middle. Code is going to be on this right side here, and the book, which will be shown in every video, is going to be over here on this left side. What happened? Split the screen. Great. Thank you. There's a link to the book in the description. Just go to nnfs.io in your browser, and you'll get to the link where you could buy the book. You could buy an ebook. You could buy an actual copy of the book. I only have the ebook, which is a PDF that I could send across all my devices. Super, super convenient. Incredible book. Highly recommend you buy it. There will be a link in the description. Something should pop up somewhere here at some point, probably. I'll edit that like later, where you could go and buy the book. But until then, I'm just going to be following along with the book in the videos by myself, and we're going to super blow through it. So in this one, we're just going to do chapter 1, which is just the introduction. It's getting the acknowledgement, table of contents, copyright, license for code. This is my favorite feature of the book, the README. I think that's awesome. Okay, chapter 1, introducing neural networks. So you guys should have a basic understanding of neural networks going into this. You should, if you want to follow along. You could otherwise, it just might be a little bit harder. You definitely need to program, you definitely need to know how to program in Golang. There's a link in the description to a good tutorial for that. If you don't know how to program in Golang, that's not going to work. You're going to have to learn that. So, okay, good. So after you do that, come back here, and let's introduce neural networks. With a general idea. So like I said, you guys should understand a little bit of how neural networks work, but just this is a nice evener. This is going to be a short video. Chapter 1 is super easy. There's not going to be a lot of coding in this video. So let's just get down to the thing. And for this, it's just going to be me reading the book basically. But that will change in the coming chapters probably. Okay, we begin with a general idea of what neural networks are and why you might be interested in them. Neural networks, also called artificial neural networks, though that is probably redundant actually now that I think about it, are a type of machine learning often conflated with deep learning. So they're not the same. A neural network is not the same as deep learning. The defining characteristics of a deep neural network is having 2 or more hidden layers, a concept that will be explained shortly, so that's going to be later on. It's reasonably safe to say that most neural networks in use are a form of deep learning. So basically, summarizing that paragraph, you have neural networks, and then you have deep learning, which is a kind of a neural network. A neural network just means that there's neurons and it's a network. Deep learning means that there are 2 hidden layers. In other words, it's a deep neural network. There's a lot of stuff going on. And like it said in the thing, that's going to be explained. A brief history? No, not interested. What is a neural network? So, artificial neural networks are inspired by the organic brain, translated to the computer. It's not a perfect comparison, obviously, but there are neurons, activations, and a lot of interconnectivity, even if underlying processes are quite different. And they're incredibly different, like a ton. In fact, this model is deceptive on how similar a node in a neural network is to a neuron. They're not at all similar. At least this is deceptively similar. They are similar, but not this much. Not this similar. Like this makes it look like this thing is exactly like this thing. No, none of that's true. But anyway, moving on. It's just a cool thing. I mean, you know what? I don't even know what I'm talking about. They could be this similar. I just don't think so. I've learned more about neurons recently, and it seems like they're far more complex than I ever imagined. Whereas these things are actually quite simple. But anyway, he said it's not a perfect comparison, so that's fine. A single neuron by itself is relatively useless, but when combined with hundreds or thousands or many more of other neurons, the interconnectivity produces relationships and results that frequently outperform any other machine learning methods. This is true. And here we have an example of this is a deep neural network, bunch of stuff. This might not make sense to you if you don't know what a neural network is, but someone that knows what it is, someone that's coming from like TensorFlow or PyTorch, you guys should be very comfortable with this kind of model. And this kind of thing will be explained later, I imagine. The above animation, so there's an animation that you could go to, shows the examples of. Oh, by the way, you guys should, and I should actually add this in the description. Sorry, I completely forgot about this. You guys should check out the author wrote, not the author. The author. The author made a playlist. Tutorials, basically going through his book, but in Python. So I'm going to link that. Dex. Sorry. Nope, that doesn't make sense. I forgot his channel name. Sent Dex or something like that. There we go. Playlists. Oh my god, all his stuff looks so similar. Here we go. Playlist. There you go. This is the thing. This is the thing. And boom. And I just want to copy this. Okay, let's save that description. Excellent. And I want to go over here. And I want to go over here to where my YouTube stuff is, just so I don't always have to do it. And let's paste that in. Great. So now that's going to be there for the next video. Excellent. Anyway, moving on. Sorry about that. Oh, and this should also go away. Goodbye. Okay. Okay, it might seem rather complicated. Neural networks are considered to be black boxes, and that we often don't actually know why they're reaching the conclusions. We do understand how they do this, though. So we don't understand like how. Yeah, it's like a human brain. We don't really know exactly what's going on, but we understand like how it's thinking about things in a way. By the way, look at how cool this barcode is. It's got like connections over here. I've never seen that before. That's interesting. Anyway, it might seem rather okay. Dense layers, the most common layers, consist of interconnected neurons. In a dense layer, this is so not good at explaining things if you don't know what's going on. We should probably watch the animation. Visualizing neural networks. Yeah, let's make this a bit bigger. So you see we have an input layer, and that's connected to all these hidden layers with an output layer. And you see these are all the weights. Weights are basically lines, essentially. And biases go for each, well, anyway, change that. So this is an even bigger neural network. What's that sound? It's not coming from my computer. It's weird. Anyway, here's an even bigger neural network, so it's massive. Anyway, once we start coding this stuff, we'll make a lot more sense. What is that? Give me a second. Sorry about that. Very unprofessional of me. You guys probably couldn't even hear that, but I could hear it. Moving on. It was just a computer in another room making some noises. I don't know. Anyway, moving on. Okay, let's take a look. Okay, here we go. Dense layers, the most common layers, consist of interconnected neurons. So the neurons, each neuron, there's a bunch of neurons in a layer, and they're all connected. In a dense layer, each neuron, the neurons in the layer are not connected. The neurons in the layer are connected. They're all connected to a neuron in the next layer. There are 2 layers, and they're connected. Each neuron of a given layer is connected to every neuron of the next layer. So every single neuron of one layer is connected to every single one of the other layer, which means that its output values become an input for the next neurons. So if you think about it this way, then an input is going into each neuron. So this neuron outputs a number, and that one goes in as an input to each neuron of the next layer. Each connection between the neurons has a weight associated with it, which is a trainable factor of how much this input to use, and this weight gets multiplied by the input value. So these lines that I'm drawing, that a neuron is connected to all the other neurons, that line is basically a number. It's a weight, and it could be like 0.5. In other words, take this input value from this neuron and just times it by 0.5 and then pass it into this neuron. And this one could be like 0.7, and this one could be like 1. Like use all of this input for the next one. That's very similar to how our brains work. And we could tweak those numbers, and that's basically how we tweak our neural networks. Once all of the input weights flow into our neuron, they are summed. So this neuron, for example, is getting an input from this neuron, this neuron, this neuron. So once it gets all of those times by the weights, all of those not factors, but products, all of those products are added up together, and then and a bias. So each neuron has its own bias, and then we also add that bias. It's like, imagine a slope of a line. So think about the mx part as being all of this, and then the plus b part being the bias. It's a bias. The purpose of the bias is to offset the output positively or negatively, exactly like a line, which can further help us map more real-world types of dynamic data. In Chapter 4, we will show examples of how this works. So again, most of this stuff seems complicated now, and I can understand why it might be complicated, but as we start coding it, you'll develop the intuition of this stuff. This is just to try and give you a basic introduction, which might even be confusing you more. I have no idea. Hey, look, my email is here, because this is my copy. That's crazy. So I understand why it might be complicated. As we start coding it, you'll get a sense of it. In fact, honestly, if I didn't know what a neural network was, this introduction would probably freak me out more than help me. But that's probably because I'm just skipping a lot of parts of it. Okay, the concept of weights and biases can be thought of as knobs that we can tune to fit our model to data. So the weights and biases are all numbers, and basically the only part of our neural network that we'll be tweaking to make it perform our task better is those values. We're turning the knobs, essentially. We're tweaking those values, if you can imagine a big machine. In fact, you should watch CGP Gray's video, CGP Gray, How Machines Learn. This is an excellent video to watch, give you a basic understanding of how neural networks work. You should watch this one as well. This is the kind of thing that we'd be dealing with, how machines really learn. That's the kind of neural network that we're dealing with in this video. So yeah, go watch this video. Because he uses the knob analogy. That's what it made me think of. We often have thousands or even millions of these parameters tuned by the optimizer. The optimizer is the thing that tunes stuff. Some may ask, Why not just have biases or just weights? So why do we need both the weights and the biases? Again, the weights are these lines essentially, and the bias is for each neuron. Each neuron has a bias. Biases and weights are both tunable parameters, and both will impact the neuron's outputs. So they have that in common, but they do so in different ways. Since weights are multiplied, they will only change the magnitude, or even completely flip, because if you imagine we multiply by -1, even completely flip the sign from positive to negative, or vice versa. So output, the output of every neuron equals the weight times the input, or all of the weights times all of the inputs, plus bias. Is not unlike the equation of a line. So exactly the thing, y equals mx plus b. We can visualize this with, there you go. So the weight could say is 1, the bias is 0, and this is what, so y equals mx plus b, exactly. So x would be the input, times 1 is just x, and then the bias is 0, so nothing happens. Graph of a single input neuron's layer, oh yeah, exactly. Adjusting the weight will impact the slope of the function. As you can see, this is times 2, so this would be 2x plus b, which is 0, so it's just a line with a slope of 2. As we increase the value of the weight, the slope will get steeper. If we decrease the value of the weight, the slope will decrease. If we negate the weight, the slope turns to negative. So as you can see, it's just functioning like a normal line. And you can see the weights and the biases. So this is when a bias starts getting involved. This should give you an idea of how the weights impact the neuron's output value that we get from inputs times weights plus bias. Now, how about the bias parameter? The bias offsets the overall function. For example, with a weight of 1 and a bias of 2, we get this. So this is a normal 1x1 line, 1x1, but a line with a slope of 1, with a bias of 2, and it's just bringing it up. So you see how it just offsets everything, which is exactly what a bias does. As we increase the bias, the function output overall shifts upward. If we decrease the bias, then the overall function output will move downward, as you can see. As you can see, weights and biases help to impact the output of neurons, but they do so in slightly different ways. This gives you a sense. Oh wait, hold on. This will make even more sense when we cover activation functions in Chapter 4. Chapter 4 is an important chapter, apparently. Still, you can hopefully already see the differences between weights and biases and how they might individually help to influence output. Why this matters we will convey shortly. Great. How much longer is this chapter? Because I want to get to the coding part. Not that much. Let's see what else he has to say. Okay. As a very general overview, wait, this is an activation function. Why are we talking about activation functions so soon? I guess this is just a very quick summary of neural networks. As you can see, weights and biases help to impact the output of neurons. Okay, very good. As a general overview, the step function meant to mimic a neuron in the brain, either firing or not. So our neurons in our brains, kind of you could simplify to they fire, like they send an electric signal, or they don't fire. In other words, they don't send an electric signal. So the step function basically does this. The step function takes in any input, and if it takes in any input, the input could be an output from another neuron. So a neuron outputs, let's say, 20. The step function will look at that and say, okay, listen, if you're above 0, you're 1. You are now 1. If you're below 0, you are now 0. In other words, if you're above 0, if your output is above 0, you have fired, and let's just convey that with a 1. And if you're below 0, in other words, you're a negative number, you are a 0. In other words, you did not fire, and we can convey that with a 0. In programming, an on-off switch as a function would be called a step function because it looks like a step if we graph it. As you can see, if x is below 0, it's just 0, and if x is above 0, it becomes a 1. Great. For a step function, if the neuron's output value, which is calculated by, so here, this would be an example of a neuron's output. It's the sum of all the inputs times all the weights, it's the sum of all the inputs times their respective weight. So you have all these inputs, 1, 2, 3, 4, 5, and each one of them has a weight. Maybe I could draw this actually, that might be helpful. Paint. Nope, 2 B's, just one. Paint. Let's see. Okay, let's get a circle here. Actually, let's get several. 1, 2, 3, 4. Let's get another circle. Or nope. You need to still be a black circle, Mr. Circle. I don't know why everything is just slowly going off center. That's better. Okay. And then let's get another circle, and this circle will be orange. Or red. Red's nice. Okay, and now let's get a line going. No, no, no. Let's make the lines. Let's make the lines like, I don't know, blue. Okay, and then let's just put a bias over here. So like a beacon big with a B. I don't know. So these are all the inputs to the neuron you could imagine, and these could be another layer. These could be like a hidden layer, and the actual inputs could be over here. But let's just say these are the inputs to our red neuron. This is our neuron. Wait, why are you? Hold on. Excuse me. How do I get out of here? I don't even know. Oh wait, it's the selection tool. Nope, not even the selection tool. I have no idea. Okay, so no, this is bothering me. Just gonna draw over it. You are supposed to be blue. Thank you. Okay. So imagine these are all the inputs. These all have a value, some random value. Well, it's not actually random, but let's just say it's a random value. This one could be like 0.1, 0.2, 0.3, 0.4. These are all weights. So these are all another random value. And this is going to be multiplied by this weight. This is going to be multiplied by this weight. This is going to be multiplied by this weight. This is going to be multiplied by this weight. You can visualize that in the neuron, all of these products are added together. And then the bias that's in the neuron is also added to the final thing. So as you can see, it's the sum of all the inputs times their respective weight. The blue lines are the weights, plus the bias. And that's going to be the output of a neuron. So if that output is greater than 0, then the neuron fires. So it would be a 1. Otherwise, it does not fire and would pass along a 0. The formula for a single neuron might look something like this. So this exactly would be a single neuron. The output, our orange circle, which I deleted now, which is very sad, but the output of our orange circle equals the sum of all the inputs times their weights plus a bias. We then usually apply an activation function to this output, noted by activation. So output equals activation of output. And a step function would be a kind of activation. While you can use the step function for your activation functions, and some people do that, and it's a very simple function, very quick, we tend to use something slightly more advanced. The neural networks of today tend to use more information activation functions. So an activation function that conveys more information. For example, all this activation function does is tell you whether or not the input was below 0 or above 0. Rather, today, we use something called a rectified linear function. In other words, it's a linear function, which would basically mean y equals x, but it's been rectified, which you will see what that means, which we will cover in depth in Chapter 4. Okay, apparently you won't see what that means. We'll cover it in Chapter 4. Each neuron's output could be a part of the ending output layer. I don't even know what that means. Each neuron's output could be a part of the ending output layer. Right, so every neuron could be the final layer, or rather every neuron could be a part of the final layer, the actual outputs that you get. That's possible. That is one possibility. As well as the input to another layer of neurons. So you can imagine here's the layer of neurons that got their inputs and then went through this whole mess over here. Here's a layer of neurons. They got their inputs, went through the mess. Every neuron got its output, and then you could imagine that these would now all be brand new inputs for another layer over here, and then that one could be brand new inputs for like the actual output layer, which you get your actual results that you want. And look at that, he's actually going to give an example, so great. While the full function of neural network can get very large, let's start with a simple example with 2 hidden layers of 4. Okay, so here we have inputs. These would be numbers. Every input is connected to every neuron, as you can see with a weight. So the lines are weights, just like I showed before. And these are all the neurons of the new layer. And so every single one of these layers would do their own mess over here. And then they would do that. And then these would be the new inputs for this layer. And then these would be the new inputs for this layer. And that's a neural network. Or rather, this is a deep neural network, I believe. Oh no, this is a basic neural network. I don't even know. The terms are confusing. They also don't really matter. Anyway. Along with these 2 hidden layers, there's also 2 more layers here. The input and output layers. The input layer represents your actual input data. So let's just say, I was literally about to say this. I was about to say pixel values from an image. I was about to say that. For example, pixel values from an image. See, you could just buy the book. You could just buy the book and follow along in Python. The point of this series is to do it in Golang, but we're not doing that yet. So you could literally just buy the book and read the book. I recommend buying the book. It's a great book. Not sponsored, by the way. They're not actually sponsoring me. I just think that it's a great book. Okay, so for example, pixel values from an image or data from a temperature sensor. Yeah, he used this example in his videos. I remember he always said temperature sensor. I don't know why he did this, because I guess maybe he was building his computer and he was thinking a lot about temperatures of his computer parts, but this was not something that I could relate to at all. I was focused mainly on this, pixel values from an image. By the way, when I say he, I mean Harrison, the guy that made the book, who also made the tutorial series that you can find a link to in the description. Okay. While this data can be raw, in other words, in the exact form it was collected, in other words, you could get, like, let's say the sensor is 30 degrees, so you pass it in 30 degrees. You will typically pre-process your data through functions like normalization and scaling. This is long. Is he just gonna say exactly what I could do in better words? Not better words, but in more casual talking words. No, let's just read it. And your input needs to be in numerical form. Concepts like scaling and normalization will be covered later in the book. They're very useful and very important. Don't forget to normalize your data, okay? It will break everything. Not break, but things will be much harder. However, it's common to pre-process data while retaining its features and having the values in similar ranges between 0 and 1. So basically, when you have, like, let's just say pixel values, all pixel values in all computers are arranged between 0 and 255. Let's just say it's a black and white. So every pixel has one value from 0 to 255. We don't want to pass that into our neural network. We don't want to pass a value of, let's say, 230. What we want to do is we want to pass a value from between 0 and 1. So for example, if the pixel value was 255, we would pass in a 1. If the pixel value was 0, we would pass in a 0. This is called mapping. You map all the numbers. The easiest way to do this in this exact example that I'm talking about, which is pixel values, is you just divide the pixel value by 255. You divide the pixel value by the highest number it will ever get to. That way 255 is a 1, 0 is still a 0, and everything in between gets scaled accordingly, which I guess you would call scaling or normalization, same thing. So we want to pass in something between 0 and 1 or negative 1 and 1. Negative 1 and 1 also works. To achieve this, you will either use both scaling and normalization functions, so there are functions to do all this. The output layer is whatever the neural network returns. Oh, that's it. Yeah, okay, this should be a new paragraph, I guess. The output layer is whatever the neural network returns. With classification, where we aim to predict the class of the input, the output layer often has as many neurons as the training data set has classes, but can also have a single output neuron for binary, two-class classification. I guess that's true, yeah. I don't know if that makes sense in English. This is like an academic book, so it doesn't sound like he would talk. Like he wouldn't talk like this in his tutorials, which is fine. That's why I'm here. We'll discuss this type of model later, and for now focus on a classifier that uses a separate output neuron per each class. For example, if our goal is to classify a collection of pictures as dog or cat, then there are two classes in total. Right, so if you have, again, let me just repeat that in normal English. If you're making a neural network that you want to pass in an image, and the neural network will spit out, is this image a dog or is this image a cat? What you would do is you would have as many inputs as there are pixel values in your image. Each input would get a pixel value. That would pass in through its neural network, and then you would have two neurons as the output layer. You would have an output layer of two neurons, as you can see here, and this one would be like, if this one is a 1, then it's a dog, and if this one is a 1, then it's a cat. And the neural network is going to predict. What he says over here, which is that for output neuron, having a single output neuron for binary classification, you could think about it that instead of having two neurons here, this one is dog and this one is cat, you could have one neuron. And if the neuron is above 0.5, if it returns a value that's above 0.5, then it's a dog. If it returns a value that's below 0.5, then it's a cat. Excellent dog and cat example. Hope that made sense. Okay. This means our output layer will consist of two neurons, one neuron associated with dog and one other with a cat. Now he's just repeating what I'm saying. See, it's clear that I've read the book. Like every example I'm giving. Although in fair, the dog and cat one I read it before I gave the example, but I would have given that example anyway. You can also have just a single output neuron that is dog or not dog. Dog or not dog. That's funny, actually. Yeah, I didn't think that it could be dog or cat. It could just be dog or not dog. Yeah, fine. Okay. Oh, here we go. Now it's the visualization. So here, these would be all the pixel values, and this would be the image. Oh, look at that. See, that's him. That's the author right there. That's a picture of the author. Great guy. I think. I've never met him, but I don't know. He's always happy in his tutorials, I guess. Except I remember one tutorial where there was one tutorial he made where he drank a cup of coffee and then mentioned something about someone commenting that he shouldn't drink while he makes tutorials, and he was like, stupid commenter. And I was like, yeah, I guess that is a stupid commenter. That's the only time I ever saw him get slightly close to mad, but he wasn't mad, he was smiling. Anyway, this is not important at all. Point is, I'm pretty confident he's a very happy guy. Oh, thank you, Big Squeak. Sorry if I didn't see this until recently and you're not here anymore, but anyway, appreciate that. Hope to make many more. I love Golang, my favorite language in the whole world. Wish I knew how to use it better. Okay, so here we go. So this would be a picture passing through the neural network into the hidden layers. Output, you see these two neurons, and this is outputting a dog. And I guess they're showing it as being, this circle is more filled in, so this one is the one that's chosen. That does not look like a dog to me, but then again, yeah, no, it's just very small. I thought it would have been like a lump of mud. Anyway, dog. I love dogs. Oh, look, math. Terrifying, right? Isn't that horrifying? And look, there's a random negative over here. You gotta remember the negative. Okay. So there you go. So that's just an example of classification. The thing that makes neural networks appear challenging is the math involved and how scary it can sometimes look. See what I say? Look at this. This looks absolutely horrifying. This looks horrifying. There are all these symbols, linear algebra, terrifying matrices. We have symbols on top of symbols. It just looks terrifying. For example, let's imagine a neural network and take a journey through what's going on during a simple forward pass of the data. Don't say things like forward pass before you explain what that is. A forward pass is the, shoot, now I don't know how to explain it. The inputs go in, the outputs come out. That's a forward pass. It's going in that direction. Inputs to outputs. The backward pass is what we do to train our neural network, which we will get to later, because there's no way I'm explaining it here, mostly because I don't really understand what's happening. But anyway, forward pass. Forward pass is when you're passing an input and getting the output. And the math behind it, great. Neural networks are really only a bunch of math equations that we programmers can turn into code. For this, do not worry about understanding everything. You shouldn't. The idea here is to give you a high-level impression of what's going on overall. Don't try to understand everything. You need to take like a linear algebra course and calculus at the same time. And I haven't done either of those. I don't actually know how neural networks work. I just know how to program them. I don't actually know what I'm doing. That's why I kind of want to do this tutorial series, because I'm hoping that I'll have to do more. Don't worry, still here. I may not be able to catch the videos live. Yeah, don't worry about catching them live. No, absolutely don't worry about catching them live. They're going to go up as full videos, and you can watch them anytime. The only reason why I'm doing it live is so that I don't have to worry about uploading it. Don't worry about catching it live. Don't worry about it. Stop worrying. Okay. The idea, okay, very good. Then this book's purpose is to break down each of these elements into painfully simple explanations, which will cover both forward and backward passes involved in training neural networks. That's actually good, because I need a review on backward passes. I don't actually know how to do it, because in most libraries in Python, like TensorFlow and PyTorch, you just do like optimizer dot backward, and that's it, and like that's all you have to do. So I don't actually know what I'm doing. You just have to remember. You just have to memorize what to do. When represented as one giant function, an example of a neural network's forward pass would be computed with this monster. There's a log, things are on top of each other, because that's how sums work. There's a upside down A, which I don't even know what that means, because I don't know math at that level. And also, yeah, this negative is interesting. I want to learn more about why this negative is here. I don't remember exactly why that's there. Naturally, that looks extremely confusing. Yes, it does. This looks ridiculous. Like, what the heck? And the above is actually the easy part of neural networks. Yeah, the forward pass is actually the easy part. That's funny. This turns people away, understandably. In this book, however, we're going to be coding everything from scratch. And when he says scratch, he means using NumPy, which is not Scratch. We are doing it from scratch. There is no NumPy for Golang, I think. I'll do some research before I do the next video and see if there is a NumPy for Golang, or rather, I'll do some research in the moment when we need to use NumPy and see if we could find some package or something in Golang. If not, we'll just have to program it ourselves, which will be fun. So when he says from scratch, he's lying. He's not actually doing it from scratch. From scratch would be, well, I guess from scratch would be with wires, and you're just attaching wires. So we'll allow programmers to say that when they use NumPy, they're programming neural networks from scratch. I think that's valid. And when doing this, you should find that there's no step along the way to producing the above function that is very challenging to understand. For example, the above function can also be represented nested Python functions like this. I'll be honest with you, I remember this moment when I was watching his tutorials and he broke it down from this to this, and my face smiled. I was like, oh my god, I know what every single one of these are and what they do, and it's amazing. Again, notice our little negative over here. And there you go. This is what it would look like in Python code. And honestly, to me as a Python programmer, this looks a lot less scary. And yeah, most of this stuff I don't know how to do in Golang though. Like there's the sum thing, which I guess we could use Golang's built-in sum function, but it's matrix summing, so it's different. And then there's also the dot product, and I'm not sure how we're gonna do that. And yeah, we'll be able to do all of it. It's just a matter of how much work each step is gonna take. Like, will we just import a library, or will we have to code it ourselves? Okay. There may be some functions here that you don't understand yet. For example, maybe you don't know what a log function is, but this is something simple that we'll cover. Excellent. Then we have the sum operation, an exponentiation operation. Again, you may not know what exactly this does. Which one is he talking about here? Here, mp that expo, that exp. Then we have a dot product, which is still just about understanding how it works. There's nothing there that's over your head. You'll be able to understand all of this. It's actually kind of easy. Finally, we have some transposes noted as T. Yeah, transposing is going to be interesting. I wonder how we're gonna do that in Golang. Yeah, transposition is going to be easy because in NumPy it's super easy to do transposition. You just put in a T. Which again, once you learn what that operation does, it's not a challenging concept. It really isn't. Like, it's a simple operation. You just need to know the name. It's like learning a new. It's like learning a new word. It really isn't that much math. It's not that complicated. What you get? Okay. Once we've separated each of these elements, learning what they do and how they work, suddenly things will not appear to be as daunting or foreign. Nothing in this forward pass requires education beyond basic high school algebra. For an animation that depicts how all of this works in Python, you can check out the following animation, but it's certainly not expected that you'd immediately understand what's going on. The point is that this seemingly complex topic, he means this, can be broken down into small, easy to understand parts, which is the purpose of the coming chapters. Excellent. And I don't think we need to do the animation. A typical neural network has thousands or even millions of adjustable parameters. By the way, that may sound like a lot. In our brain, we have trillions of neurons. I'm not even, literally trillions. It's crazy. It's crazy. So when we say things like millions of adjustable parameters, our brain has, I guess in terms of adjustable parameters, our brain has a ridiculous amount. And that's insane. That's crazy. I think it's awesome. I think that our brains are just as fascinating as the universe. Truly. Okay. Great. In a way, neural networks act as enormous functions with vast numbers of parameters. I remember when I was first learning about machine learning, I was like, oh my god, a neural network is basically like a function that just codes itself. And yeah, it's very similar to that. The concept of a long function with millions of variables that could be used to solve a problem isn't all too difficult to understand. It's just a very big function with a ton of parameters, and it's doing things with all those parameters. And the best part is you never have to touch those parameters. We're going to build something that will touch them for you. And that thing is very easy to build. In CGP Gray's video, it's called BuilderBot. That's BuilderBot. BuilderBot's job is to adjust things. Or rather, knob adjuster bot. Anyway. The end goal for neural networks is to adjust their weights and biases, the parameters, so when applied to a yet unseen example, that's a key point which we'll cover, in the input, they produce the desired output. So when they see a picture of a dog, they say it's a dog. When supervised machine learning algorithms are trained, we show the algorithm examples of inputs and their associated desired outputs. None of those made sense to me as a coherent sentence. Let's read that again. When supervised machine learning algorithms are trained, okay, we show the algorithm examples of inputs and their associated desired outputs. Yeah, okay, fine. Not entirely sure what he's saying in that sentence, but I don't think it's too important. One major issue with this concept is overfitting. Oh, he's explaining why the yet unseen example is important. When supervised machine learning algorithms are trained, we show the algorithm examples of inputs and their associated desired outputs. Very good. So I don't understand why I can understand that. When we train a neural network, we show them the input and we show them the output. And we say, this is the input, this is what the output should be. Go adjust yourself so that you output it correctly. And the neural network's like, okay, I'm adjusted to do that. And then we showed another one, another picture, another desired output, and we say, now adjust yourself to this one. And and there you go. And I'm simplifying it. We use batches and stuff, which we'll cover later. But the point is, we're nervous of overfitting because we don't have overfitting when the algorithm only learns to fit training data but doesn't actually understand anything about the underlying input-output dependencies. One thing that could be problematic is if we show it the same picture so many times that it doesn't actually learn to generalize things. It just says, when I see this exact picture, I will say dog. And we don't want that. We want it to understand general ideas. Like when you see a dog's kind of ears, that means it's kind of a dog. When you see a dog's kind of face, that means it's a dog. We want it to understand general things, not the specific pictures it's seeing. And when a neural network only understands the specific pictures that it has seen, it's called overfitting. Okay, very good. The network basically just memorizes the training data. Exactly. And by the way, kids in high school will do this too when studying for a test or something. Thus, we tend to use in-sample data to train a model and then use out-of-sample data to validate an algorithm. Certain percentages are set aside for both data sets to, okay, very good, I'll explain all this easier. Yeah, okay, I'll explain this entire paragraph. When we're training the thing, we have a ton of images to train it on, and then separately, we have a bunch of brand new images to test it on. We train it on these images, and that's most of the images. We have, like, let's say 100,000 images for training. And we give it to it, and we show it picture, output, adjust yourself so that you're always getting stuff right for this. And then it's like, okay, I'm always getting stuff right for your training stuff. And I'm like, did you memorize it though? Are you just such a big neural network that you've been able to memorize all of these things? The only way I could test that is I have these over here, let's say it's 10,000. So 100,000 to train on, 10,000 to test on. This is an image you've never seen before. You cannot memorize this one. You cannot have memorized this one because you've never seen it. What do you think this one is? And we show it to it. And it goes, I think this one's a dog. And I'm like, very good. You understood. You've never seen this image before, and yet you got it right. And there you go. So that's the idea of we train it on most of our images, 100,000 say, and then we test it on the other another 10,000, let's say. Maybe I'm getting the exact numbers wrong or something. Yeah, I guess he's saying, imagine you have 100,000 images, you train it on 90,000 of them, and you test it on 10,000 of them. This is called generalization, which means learning to fit the data instead of memorizing it. The idea is that we train, slowly adjusting weights and biases, a neural network on many examples of data. When we take out of sample, when he says out of sample data, he means like the testing data. Data that the neural network has never seen before. Oh, there you go. That the neural network has never been presented with. Use the word presented as opposed to seen. Okay, and hope it can accurately predict on these data too. You should now have a general understanding of what neural networks are, or at least what the objective is, and how we can plan to meet this objective. To train these neural networks, we calculate how wrong, okay, this is important. To train these neural networks, we calculate how wrong they are, using algorithms to calculate the error. These are called loss. They're called loss algorithms. In other words, we see, okay, here's the input. What do you think the output is? It says, I think the output is this, and we say, no, the output is this much. How wrong were you? And we basically use how wrong they were to attempt to slowly adjust their parameters so that over many iterations the network gradually becomes less wrong. We're always looking to decrease the loss, decrease how wrong the neural network is. The goal of all neural networks is to generalize, meaning the network can see many examples of never before seen data and accurately output the values we hope to achieve. Neural networks can be used for more than just classification. They can perform regression, predict a scalar, singular value, clustering. By the way, regression is mostly used in things like reinforcement learning as opposed to classification. But anyway, that's a separate conversation. Clustering, assigning unstructured data into groups. So here we have a bunch of data. It's like a blobby. I want you to draw groups of this data. Clustering is complicated. Watch a tutorial on clustering. And many other tasks. Classification is just a common task for neural networks. Classification is a common task. It's also a big breakthrough because people didn't always think that neural networks would be able to look at an image and understand the image. And that was a big breakthrough. And also it's super easy to understand. There's a phone ringing. Let me turn that off real quick. Sorry, the spam people got it. We have a company that basically is like, this telephone will be spam, and so it stops ringing. Anyway, why was classification interesting? Right, it's a breakthrough, and also it's very easy for a human to understand. We showed an image, and we ask it to say, are you a dog or a cat? Excellent. End of chapter 1, finally. That was the introduction, hard introduction, a lot of information thrown at you. Take time to digest it. Write in the comments any questions, comments, concern, anything like that. I'm going to be making a playlist of this, which is on the channel. Again, link to the book is in the description. Highly recommend you check that out. I'm serious, highly recommend. How much is it? It's like, I think it's even less than $100. NNFS. Yeah, NNFS.io, less than $100 for the for even a hard copy of the book, which is excellent. For the ebook, it's $30. $30 for an ebook, and the knowledge you'll get from this book will be invaluable for many incredibly high-paying jobs. It's an excellent book. Highly recommend you check it out. Until next time, the next video we'll get into chapter 2, coding our first neurons, and I think I'm gonna start doing that instantly. So I'm gonna end this stream and then start a new stream, I think. So where do we do this? Right, end stream. See you guys around. Check out the next stream and the next video in the playlist if you're coming here afterwards. Hope you enjoyed, and